Deep learning models ingest chaotic, unstructured data, raw text, scattered audio, and messy images, and pull them into a rigid, highly organized neural grid. In rigorous benchmark tests for computer vision and natural language processing, these architectures routinely achieve accuracy rates over 95%. This performance creates intense pressure on enterprise leadership to deploy. The promise of automatic feature extraction suggests a massive shortcut to identifying complex market patterns. However, nearly 40% of enterprises that attempt to integrate deep learning fail, largely due to extreme technical complexity and escalating operational costs. While adoption continues to climb, this jagged bar chart shows a 56.4% spike in reported AI incidents over the past year. Organizations readily identify privacy and security as primary threats, but their active mitigation efforts consistently lag behind their implementation schedules. Decision makers are trading manual control over their systems for high-tier performance, often before the long-term organizational costs are fully calculated. Adopting deep learning without a rigorous, operationalized, responsible AI framework creates an institutional liability that often outweighs the performance gains. Determining if that risk is acceptable requires mapping the physical requirements of these models against their actual outcomes. Our deep learning ROI matrix begins with the first operational pillar, data quality. This starts with a requirement for millions of high-quality, labeled data points. This massive data input enables automated feature extraction, allowing the system to scale its capabilities and refine its predictions as more information becomes available. The trade-off is a heavy resource drain. Data curation typically consumes 80% of total project time, and poor quality inputs can drop model performance by over 25%. The second physical barrier is the capital requirement for compute and infrastructure. Training these networks demands specialized hardware like GPUs or TPUs, which carry exorbitant upfront costs and ongoing energy requirements. This infrastructure allows an organization to process unorganized datasets and achieve state-of-the-art results on global AI benchmarks. However, the training process often takes days or weeks, which can neutralize an engineering team's ability to perform rapid, agile iterations. Deep learning relies on the brute force of capital and time, effectively pricing out organizations that lack high-performance computing setups. The third operational barrier in the matrix is the structural black box nature of neural networks. These systems utilize multi-layered hierarchical networks to process data through millions of hidden connections. This architecture successfully identifies complex patterns and relationships that remain invisible to human analysts. The trade-off is a loss of explainability. When the model makes a critical error, it is often impossible to trace the internal logic behind the specific output. In sectors like healthcare or finance, this lack of transparency can destroy regulatory compliance and erode user trust. Managing this risk requires the fourth pillar of the matrix, responsible AI governance. This involves instituting rigorous adversarial testing and strict factuality benchmarking, using tools like Simple QA. These measures provide vital protection against adversarial attacks, data leaks, and hallucination incidents. However, building this governance structure from scratch slows time to market, and most organizations currently lack the maturity to execute it. Data from the Stanford AI Index confirms this gap. Looking at the operational maturity levels 1 and 2, most organizations still have limited or no formal mitigation measures in place. The bureaucratic and operational drag required to build a risk management framework represents a larger, more persistent organizational cost than the physical hardware. We can now map the specific conditions where deep learning makes financial and operational sense. This matrix evaluates the regulatory and data burden on the x-axis against the complexity of your unstructured data on the y-axis. The top left quadrant is the green zone, where deep learning deployment is most effective. You belong here if you are processing massive volumes of unstructured data, like video files for computer vision, or extensive text for natural language processing. This zone also requires an enterprise-grade compute budget and a dedicated team of specialized engineering talent. Finally, the deployment should exist in a low-regulation environment, like a retail recommendation engine, where the cost of a wrong prediction is minimal. The bottom right quadrant is the red zone, where deep learning should be avoided. Organizations fall into this zone if they rely on structured data like spreadsheets, operate under strict budget limits, or work in high-stakes fields that demand legal explainability. Traditional machine learning models are the superior choice here, providing 80% of the predictive value for only 20% of the operational risk. Deep learning is an expensive industrial tool. Successful deployment demands a strict accounting of the resources required versus the actual value generated.